Okay, so in this video we're going to look at some of the major experiments that were done to try and find the speed of light. We're talking about Newton's theory of light last time as a particle model, sort of acting like little bullets. We want to see what kind of possible speed it might have. Remember, they're trying to figure out, does it actually have a speed? How fast could it be? Or is light an instantaneous thing and actually has no speed, it just happens right away? So lots and lots and lots of people worked on this for an incredibly long time. We're just going to look at some of the major experiments that were done in order to try and find the speed of light. Now, one of the first experiments that is huge that was ever done was done by Galileo. And in around 1600, Galileo's idea was for him to stand on top of a mountain and get one of his assistants to stand on top of a mountain, but 1 mile apart, and they had little lanterns. And what they would do is they could flash the lanterns at each other and time how long it took for the signal to go back and forth. So Galileo would flash his lantern, the light would go to his assistant, the assistant would see it, he would flash back, and then Galileo would time how long it took for him to see the return flash, and with distance and time you can calculate speed. Okay, so he tried to time lantern flashes. Then all you basically need is a good old-fashioned DTV, and you can calculate the speed of light. Now, of course, this didn't work. Light was way too fast. Human reaction time, it just did not work out well. So it really didn't go much of anywhere with it. So it really didn't solve anything, whether finding the actual speed or knowing if there was actually a speed involved. It really didn't help too much with anything except to show that if light did have a speed, it was really fast. Okay. The next major experiment we're going to look at is actually from the late 1600s, and it's done by a guy named Romer, who was an astronomer. And of course, astronomy is huge around now with, the geocentric model, the heliocentric model, all that stuff is kicking in that you guys took in grade 9. A lot of them trying to figure out how the universe and everything is all put together. And he was a great astronomer, and he was watching the moons orbiting around Jupiter. So that's, of course, what we have here is we've got the Earth in orbit around the sun. So there's the Earth orbiting around the sun. And over here on the right, we've got Jupiter. And he was watching the moons of Jupiter. And of course, with information and records and all that kind of stuff, he basically knew when the moons should show up and not show up after they come out from Jupiter's shadow. And more specifically, one time he was looking at the moon Io of Jupiter, and he noticed one day that actually showed up late. So he was observing Jupiter's moon Io. And when the Earth was at the opposite side of the orbit, it actually took 16 minutes longer to see Io. So he observed it here, of course, and then when the Earth was on the opposite side of its orbit 6 months later, it took longer for Jupiter's moon to show up. Basically, the moon showed up late, and it showed about 16 minutes late because the light had to go that extra distance. And a lot of you guys know it takes about 8 minutes for light to get from the sun to the Earth, so the entire diameter would be around 16 minutes altogether. So the biggest thing by far from this was that the speed of light was not infinite. An actual speed of light did exist, otherwise the moon wouldn't have showed up late. Oops, disappeared for a second, there we go. So that was a really, really, really important find, that the speed of light did actually exist. Okay. Now, when you actually calculate it, it's basic DTV. You take the diameter of the Earth's orbit, you divide it by 16 minutes turned into seconds, and you can use DTV to calculate the speed. Of course, them knowing the actual diameter of the Earth's orbit, a little bit rough back then, it's been fine-tuned a lot since then, but he's only about 25% off, and that's like over 300 years ago. That's pretty good. So you have to respect what he was able to do. And the biggest part by far, showing the speed of light actually did exist. Now, when we get into like a couple hundred years later, mid-1800s, this is where mechanical advantage really starts to kick in. And we've got a guy, looks kind of like a French name, Fizeau is what it kind of looks like. They started using mechanical advantage. And what he basically did is he used a spinning gear. And the idea was shine light through or between two teeth of a gear. The light's going to go through the opening, it's going to bounce around on the other side, and then it's going to come back. And by the time it comes back, the gear has turned a little bit, and the light will return through the next opening between the gear teeth. So if the gear is going too slow, the reflected light is just going to hit the gear tooth and get blocked and you won't see anything. But if the gear is going fast enough, by the time the light goes through an opening and reflects around, if the gear is fast enough, the next opening will have taken its place and you'll see the light come back out the other side. Okay, so he reflected light through sequential spinning gear teeth. Now, it's kind of crazy, but the beam of light actually went over 5 miles. You need to give it a good distance in order to give the gear time to actually move into position. And then he used the spinning frequency because he knew the frequency of the spinning gear tooth, or the spinning gear, so he could get the time from that. He had the distance, you got time. DTV, you can calculate the speed of light. And he's only about 5% off the value that we use today. So that is absolutely incredible. Now, a few years later, around almost the same time, another guy, I think it looks like Foucault, which is probably Foucault or something like that, did a very similar idea, except same idea, except he used the frequency of a spinning mirror. So light hit the mirror, the light bounced around, and then it came back, and then he used the frequency of a rotating mirror to get the timing. So very similar idea as the previous experiment, using frequency of a spinning object in order to get time. Distance and time, you can get speed. Okay. Then in the 1920s, a sort of a combination of these ideas. Actually, it's sort of like a combination of just the previous experiment and Galileo's experiment, using a spinning mirror idea, except using distances between mountains. And Mitchellson in the 1920s, he actually did an experiment where he had a source of light, and the source of light hit a mirror, which reflected at 22.5 miles to another mountain. It then reflected off a parabolic dish and then came back. And by the time it went there and back, this 8-sided mirror had actually rotated a perfect 1/8 rotation, so it would reflect the perfect angle so you could actually see it. Okay, so again, spinning frequency mirror idea to get time. DTV, you can calculate speed. All right. So it was very similar to the previous experiment that we just looked at, but he increased the distance and used an 8-sided spinning mirror to get that frequency, to get that timing. And the mirror spun 1/8 the rotation between light interactions, and he was only 0.0013% off what we use now. So that was about 100 years ago. That's not actually that long ago. So that's pretty cool. My grandmother was alive when this actually happened, which is just crazy to me. So it's really neat how this actually worked. And they were able to get more and more accurate results. Okay, so these are some of the major experiments that are actually done. Now, but 10 years later or so, Mitchellson actually did another experiment using very similar, except he used a 1-mile vacuum tube. So he was able to use a vacuum instead of air, which made it work better. 10 trips back and forth by using reflecting mirrors. And he was only off by about 10,000 meters per second, which seems like a lot, but that's 10,000 out of almost 300 million. So it was super amazing, super well done. And this is one of the original articles that was printed based on that. Now, this is just a list of some of the experiments that were done. We looked at some of the major ones, but there's lots. I mean, there's the Galileo experiment right there at the beginning. There's the Romer experiment in 1676. Then there's some other stuff that we didn't really mention, but here's the 2 of the experiments we looked at as well, with rotating wheel and mirror. There they are. And really, sort of like the big difference is right around here, this is where the mechanical advantage stuff really, like gadgets and tools, were so much better. Here we had to use like astronomy and stuff like that to get the big distances that we needed in order to time stuff. But when mechanical type stuff really kicked in the 1800s, they could really use mechanical advantage and gadgets to start figuring it out. But then it starts going into electrical stuff. Like in the 1800s and late 1800s, this is when electricity is really being figured out, and they start using electronic type stuff and electronic doodads in order to figure it out and trying to find the speed of light. So this is where the electrical stuff really kicks in. And of course, the technology and the gadgetry gets really good. And of course, down here in the 1970s, they're using lasers for a whole bunch of stuff. So in 1978, we got 299, 79, 24, 58.8 for the speed of light. Now, of course, they've redefined the meter now to actually make the speed of light. It's no longer a decimal. It's just 299, 79, 24, 58, and that's it. And they redefined the meter based on the speed of light instead of some stick somewhere to get rid of the decimal place. So We just looked at the major experiments, but this has been one of the biggest things worked on by so many great people over a very, very long time. So some major experiments, some were just huge because they showed light could be really fast, showed that the speed of light actually existed, and it was actually, you were actually able to get it using some simple, really cool mechanical stuff. You didn't need fancy technology in the 1800s in order to actually get it. Just simple tools and gadgets and mechanics and good thinking and good problem solving, able to figure it out. And of course, with modern tech, we're able to take it to that next level.